Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm over at Siemens EDA with Jeff Meyer. Going to talk today about DFT shifting left. Jeff, the whole idea behind DFT has always been shift left. You want to design for test, and you want to do that in the design side as opposed to way down the line in the test. What's changed?
So one of the things that's changing, Ed, is the designs are growing, and 2.5D and 3D are leading to new dynamics. So the engineers that we're working with are wanting to analyze their designs up front and learn more as much as they can about them earlier in the process to be able to figure out which cores are outliers that they need to debug, and which problems they may need to solve earlier as opposed to waiting later.
So let's dig into this.
Sure.
Jeff, what are we looking at?
Ed, what we're looking at here is two views of design flows with DFT. So historically, we had RTL that would then be synthesized, and the output of that would be a netlist. It would have our DFT added to it, and then the DFT would need to be synthesized. There would be potentially an additional step after that, causing three synthesis steps. So you'd have a pre-synthesis before DFT for the design. You'd have synthesis of the DFT logic, and then an optimization step that encompassed everything, followed by scan, which could be part of the synthesis process, and then ATPG to get your final coverage and pattern count numbers.
And so when you think about this, so DFT was already at the beginning of the flow, but the other pieces that came with DFT were not.
Right, and that's the benefit of shifting left. Is now what we can do within our tools is we can read the RTL directly. We can add the DFT as RTL into the design RTL, and then from there, synthesis can be done in one shot, encompassing all of the optimization steps as well.
So you've saved cost, you've saved time, but what else can you do in this time that you've saved?
So one of the additional benefits of shifting left and using our quick synthesis technology is we can take the design and DFT that we now have as RTL, perform a quick synthesis of that, and use the output of that into scan and ATPG. And instead of waiting days or potentially weeks to run actual synthesis, we can get a quick synthesis view of the design in potentially minutes or hours, allowing engineers and designers to get that estimation of the pattern count and test coverage earlier in the process.
The designs themselves are becoming a lot more complicated. You've got 2.5D and 3D. You've got chiplets coming in here. You now have to think about this from a multi-dimensional level that you did in the past. What does that actually do in the DFT process that you have to do earlier?
Sure, and really, Ed, it's all about learning more about what you have in the design as early as you can in the process. So, 2.5D, 3D, again, it's all hierarchical. We have the ability to insert wrapper cells at RTL. We have the ability to then connect the entire design at RTL, test points to help with pattern count reduction and LBIS test coverage, all at RTL. And so these are the types of things that our customers are looking for so that they can pull their designs together at RTL and do all of that verification at RTL as well, because we all know RTL simulation runs a lot faster than gate level simulation.
These designs are very complicated, but they don't always come out exactly the way you planned them initially. So how does that affect what you're doing in DFT?
And that's a good question. Where that allows us to shine is that as the design changes, you can adapt DFT to the design. And so you no longer suffer from having to do all of your ECOs and then change the DFT logic late in the game.
As you started getting into 2.5D and 3D designs, though, DFT becomes significantly more important, right? Because you can't necessarily get to all these parts that you need to test for.
Right. And that's where test points at RTL is helpful, especially with your last question. As the design changes, because a lot of the controllability structures, they may change because with the 2.5 3D circuits, they may not be accessible. We need to add test points into the design to improve logic BIS test coverage, to make the designs more testable. And so really adding the test points at RTL is the best way as the designs change so that all of the DFT logic can continue to adapt to the design as it changes.
So basically, what you're doing here is you're starting out at a higher level of abstraction and working your way down right throughout the flow. So you just go, okay, what can we test quickly? How do we know this is going to work in the first place? Almost like what high level synthesis does for some of the other parts of the design. And then you start filling in the pieces and much more granularity as you go forward.
Right. And quick synthesis with our products is underpinning capability here. Because with quick synthesis, we have the ability to adapt tests on the fly. As the design changes, as you're looking to learn more about the estimated coverage, estimated pattern count of the design, as ECOs are made, we can run the design with DFT through quick synthesis and then be able to check those numbers as we go.
Where do you see engineers having the biggest problems or spending the most time when they start getting into DFT?
Great question, Ed. One of the biggest problems that we hear about is machine generated RTL. And so that's why our solutions, when you insert test at RTL, they come out as human readable RTL that don't look like it's, one construct per line, ad nauseum in the file. And it actually looks like readable RTL that you can diff from output to input and see meaningful results.
As these designs become more complex, how do you account for all that with DFT?
So one of the features that we developed for RTL test point insertion is the ability to identify areas of the RTL that are overly complicated, that have really long constructs or potentially uneditable syntax for the tools. So for RTL test points specifically, we have the ability to inform the user of which of their RTL is suitable for test points. But as a result of that, what we also have the ability to do is to analyze the design and identify those areas that are overly complicated. And then call those out. And with the visualizer inside of our tool, we have the ability to cross reference that and visualize those areas and actually directly reference the RTL.
As the chips become more complicated, as they become denser, as they get more different pieces and go up into the axis, you now have a lot more RTL that needs to be gone through in order to be able to design whatever you're doing and test. What are you running into in terms of problems there, in terms of how do you manage it? I mean, you've got complete change here that didn't really exist a couple nodes ago.
Right. And with that RTL complexity analysis, that allows the DFT engineers on a project to provide meaningful feedback to the designers of the project to help clear up their RTL and make it both manageable and testable.
Jeff Mayer, thanks for a great explanation.
Thanks, Ed.